This last video in section 6.6 is very similar to the last video in section 6.5. The only difference is I'm going to show you one problem where you solve polynomials that have complex or imaginary solutions. Now again, in order to do this, there's another theorem that's called the complex root theorem. It's very similar to the irrational root theorem. That says all complex roots come in pairs. In pairs. So therefore, if you have a problem that you solve and you know that 4 plus 2i is a solution, then its conjugate, 4 minus 2i, is also a solution to this problem. They come in pairs. Remember that. They're in pairs. Here's the problem we're going to do. I want to find all solutions to the polynomial that's written in blue. It's a 4th degree polynomial. That means I have 4 solutions. Some could be real, some could be imaginary. Well, we got to figure all these out. Well, you're going to follow the exact same procedure that we've talked about in class and that was on the section 6.5 example 3 video. Step number 1, we need to list and find if there are any possible rational solutions. So therefore, we got to follow the process that was detailed in the last video. I need to find the factors of the constant term at the very end, this minus 18 part. Well, the factors of that I'm going to list in black: plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, plus or minus 18. Now we find the factors of the lead coefficient. Well, this is easy. The lead coefficient is 1. So therefore our factors are of the lead coefficient are plus or minus 1. So what are the possible, sorry, I'm going to erase this word factors. What are the possible roots? Well, that's easy. Since this is plus or minus 1, our possible roots are right there in the black circle, because all those divided by 1 are themselves. Okay, so now step 2, we got to use our calculator and find one of the roots. Well, if you go to your calculator and type this equation in, you will get a graph that looks something like this. It appears that there are 2 rational roots. It appears one is at negative 3 and one appears to be positive 3. Well, they're both in our possible solution list. So therefore, let's pick one and try it. Let's pick negative 3. So as I showed you in the last video, you got to do synthetic division using that possible solution. So now I'm going to write my coefficients down of my polynomial. 1, 1, negative 7, negative 9, and negative 18. Looks like they're all present. Okay, draw my green line. And now, bring down the 1, and let's do synthetic division on this. I'm going to go through this quickly. You guys know how to do this. So I'm not going to spend a lot of time or take a lot of your time to do this. And upon close inspection, you'll find out that the remainder is 0. Therefore, negative 3 is a factor to this problem. And these other numbers in blue are our next factor. So I'm going to forward a slide. So we have x plus 3 is one of the factors to this problem, since the solution is minus 3. And then I got to go back. I forgot what my numbers are. I got to go back. 1, negative 2, negative 1, negative 6. So I'm going to double check this. And I believe then you have x to the third minus 2x squared. Sorry, got to go back again. Make sure I got it right. Negative 1x minus 6. That is the other factor to this problem. I'm going to go double check again, just make sure I got my numbers right. 1, -2, -1, -6. All right, good. Now, the only problem is this is a third degree polynomial, so I got to continue factoring. Well, can you factor that? Well, looking at the coefficients, I don't see any way to factor this. It's not factorable by grouping. Darn it. So I got to repeat the process. Well, going back to my calculator, going back a slide, I notice that positive 3 also seems to be a solution to this problem. So I'm going to try positive 3 on my factor that's left over. I already know this is a factor. X plus 3, I'm going to write down here in the square at the bottom, X plus 3 is a factor. Now I got to try the rest of this. So I'm going to put my numbers in. 1, -2, -1, -6. And I got to do synthetic division on this guy. So bring down the 1 and repeat the procedure. You guys know how this works. And look at that. My remainder, again, is 0. So that means 3 is a solution to the problem, which means it also has a factor of x minus 3. All right. So x plus 3 was a factor. X minus 3 is also a factor. And what's left over? What's in the circle is left over, which should be x squared plus x plus 2. And if you look at this very closely, is this factorable? The answer to that is no. Therefore, since it's a squared equation, I'm done. I can leave it. And there are my factors in the box. Now, what are the solutions to the problem? Well, we already know one solution is -3. We already know one solution is +3. We've already determined that from the graph and from our synthetic divisions. We got remainders of 0. Now I got to find the solutions to this guy. Got to use the quadratic formula. So here we go. Negative b, which is 1, plus or minus the square root of 1 squared minus 4 times a, which is 1, times c, which is 2. The whole thing divided by 2 times a, which is 1. Again, I'm using these numbers right here, 1, 1, and 2, for that problem right there, because I got to figure its solutions out. All right, well, again, you know how to do this, so I'm going to shorten the video, and I'm just going to tell you this becomes the square root of -7 all over 2. 1 squared minus 4 times 1 times 2 is -7, which is equal to -1 plus or minus, this is the square root of -1 times the square root of 7 all over 2, which equals the imaginary solutions, -1 plus or minus I square roots of 7 divided by 2. And there are your other two solutions, -1 plus I square roots of 7 over 2, and -1 minus I square roots of 7 over 2. There they are, the complex conjugates. They come in pairs. We just talked about it. And I have my 4 solutions to my problem. Well, I got to go back a slide. It was originally a 4th degree polynomial. And there are my solutions. And that is how you solve polynomials with complex solutions.